Welcome to Lecture 3, Big Data Technology and Infrastructure. So the outline of today's class is as to follow. So we're gonna walk through the big data fundamentals, which is 5 V's of big data. This is a widely accepted framework to understand the characteristics of big data, the data environment. Then we will go through the paradigms, the solid paradigm, including the distributed file system, cloud-based object stores, and data lakes. From there, then we go to the distributed framework. So that's like the MapReduce, test, Flink, which enables parallel processing across large clusters. And then we continue to the big data platforms like Hadoop, Spark, and NoSQL. And then we talk about real-time processing tools, discuss modern architectures like Lambda, Kappa for streaming analytics. In the 5 V's of big data, we start from the first V is volume. We refer to the massive amount of data generated daily, often measured in terabytes or petabytes. The second V is velocity. It is the speed at which the data created and need to be processed. This includes real-time data streaming, event logs. The third V is the variety. Variety captures the different formats of data, structure like text, JSON, logs. So the data will be like structured, semi-structured, and unstructured. The fourth V is the velocity. Velocity captures different formats of, the velocity addresses the quality of data, like noise and reliability and trustworthy of the data. The fifth V is value. Value is the most important. How organization derive actionable insight from raw data, from the massive data. So understand these attributes help us to analyze data, to selecting the right infrastructure and analytics tool, especially for designing data pipeline in industries like finance, healthcare, and smart city. Let's talk with the first V, the volume. So in the modern system, modern system must deal with like big data, like maybe up to petabyte per day of the data generated per day, especially from sort like social media platform, IoT devices, and enterprise system. Right? So this explosion of data requires scalable storage system such as Hadoop distributed file system or cloud-based object stores. So that is really big data, a very large volume of data. So we have should be handle such a large volume of data. So to handle such a large volume depend on the parallel distributed processing framework. Otherwise, the processing time would be prohibitive. So the key takeaway that traditional storage and computing solutions are inadequate at this scale. So we need horizontal scalable fault-tolerant system that can grow with data demands. Next, we discuss about the velocity, the rate of growing of the data with the data analyzed and processed. So unlike the traditional system that handle the data in batches, modern infrastructure must process data in real time or near real time. So think about the application like flood detection, autonomous vehicles, predictive maintenance, or delay in the processing could have serious consequences. This had led to the rise of streaming platform like Apache Kafka and the processing engines such as Apache Flink and Spark streaming. So these tools optimize for even time handling, allow accurate aggregation and analysis, even when the data lies out of order or late. So the challenge lies in maintaining low latency and fault tolerance while ensuring high throughput. So the next V is a velocity, variety, which is the third V of the big data. Variety refers to the diverse formats of the data encountered in modern system. Data can be structured like tablet data in relational databases, or could be like semi-structured like JSON, XML, or YAML, right? Common in the web APIs. Data can be also unstructured, including video files, free from text, the text format, social media posts like Facebook, Twitters, and could be also images. So these are the unstructured data. So this is kind of heterogeneous. Heterogeneity poses like significant challenges for integration for the data or storage, keep the data or do analysis. So traditional DBMS database kind of ill-suited for such diverse data formats, so kind of variety of formats. So instead, we use schema-less system and data lake that supports schema on read rather than schema on write. So the modern data platform must seamlessly integrate and process all types of data to provide a unified view for decision making and ML application. So now we come to the velocity, which addresses the trustworthiness and the quality of data. So in big data environments, we often deal with noise data such as sensor reading with random errors. So sometimes we have incomplete or inconsistent entries from legacy system, and some may be like biases in collected or sample data. So these issues can severely degrade the performance of AI machine learning models and lead to incorrect insight. Right? So to handle velocity, we require the data cleaning and validation pipeline, the outline detection algorithms, and robust in terms of doing data governance practices, such as like lineage tracking and auditing trails. So that means to ensure that the high data quality is prerequisite for achieving the meaningful data for the analytics later on. Next, the fifth V, the final one, the value. So the ultimate goals of big data system is not just to store or process large data volume, but to extract business value from them. This may come with the form of enhancing decision making via the dashboard of prediction through machine learning models or automation of the processes based on insights. Examples include like real-time pricing, like at Uber, personalized recommendation on Netflix, or the predictive maintenance in manufacturing. To realize value, we need the entire data pipeline from ingestion, processing to visualization and action to be aligned. We also need to measure returns on investment or ROI of our data initiatives and track KPIs tied to organizational goals. So this framework is talking about overall like the last system for big data. So in the from left to right, let's say we have the left side, we have the security. Those two we can apply like Apache Rangers to do the security of the big data ecosystem. We also have a tool for coordinate and management using Zookeeper and Emery, also the overall coordination management system. At the top, we have the Apache Assoc. This is doing metadata data management. So at the right corner, we have the tool for dealing with some data format for heterogeneous formats. You can apply like a format for Package, Afro, ORC, and Arrow. Those are the big data format that keep the binary format in column format. Okay, and then inside here we have from left to right. The first thing is processing. We have the in-memory processing, like Ignite, Spark. Those kind of tools can be used for in-memory processing. And we have streaming process, and we ingest the data. Apache Flink, Apache Storm, Kafka. Then when we analyze the data, we can use SQL or the Hadoop. We have Apache Hive, Apache Deal, and Impala. For NoSQL database, when we store the big data, we use like a group of NoSQL or HBase, or could be Cassandra or DB Mongo also. When we want to search in the big data ecosystem, we can apply like Apache Solar as search engine to go to the whole system. For data pipeline, you can use Define, Boom, and Scoop. So this is going to be like read data and then import, store into the big system, big data system. For data analytics or the machine learning part, that we need to make decisions and so on, can apply like MATLib, Mahou, Spark, MLib. It's a tool for analytics tools. And also when we do the scripting process, we could just pick, to analyze big data. It's on pick. Okay, down here we have the storage, right? In the storage, when we have big data, petabyte of data, and we can Mostly we use Hadoop distributed file system or HDFS. Hadoop comes with a resource management, which is Yarn, right? Just another resource negotiator become the greater. And also in Hadoop also have the MapReduce in order to analyze using the process for analyzing big data. In also our storage, we could use Alexio and the resource management, also Meesad. Okay, the right hand side we have the scheduler with the UCI, right? We can schedule when we have big data. We need to have the schedule in order to which one is to take control or to do the job, right? We could use also the airflow to do management. Right. So these are the kind of tools that we can use in order to like big ecosystem. But we don't need to use everything here, but we have to select which one is best for particular application. All right. Let's move on to the storage paradigms in big data ecosystem. The file system in the storage usually we use like distributed file system like HDFS, which is Hadoop distributed file system, or Google file storage, right? So these are optimized for fault tolerance, large scale batch processing, because in the way that the data, when we have big data, it's kind of segment the data to small pieces and then distribute it to the server, the commodity servers, and then it can optimize for large data. For the cloud storage, like Amazon S3, AWS S3, or it would be like Azure Box. So this offers scalability, durability, and flexible across models. Object and block storage. So object storage is suitable for unstructured and data, the metadata rich environments, and block storage is preferred for the structured workloads required for fast input output. And for the deployment models on premises system, like we would have like our local servers, right? Offer the control, but if you would like to use on the cloud, it's offer more like elasticity and cost efficiency. Sometimes we use hybrid on premise and also on cloud. Yeah. Choosing the right storage paradigm depends on your workload characteristic, also the regulatory concern and latency tolerance, and the integration with analytics platform. So this depends on the need of the organization. Let's talk about the very famous, popular with Hadoop distributed file system, HDFS. All right, so this is the most fundamental storage system, with one of the most and famous. So in the big data ecosystem, the Hadoop distributed file system is distributed. It's break large file. When you have large file, it's break into small blocks, blocks, and distributed them across multiple nodes in multiple servers that connect to in the system in clusters. It's also fault tolerance. This means it's like because when you make segments, right? You break down big file into small parts, right? So each part has multiple copies, like we call replicas. Default is 3 replicas, and then it means that when you if you have hardware failure, right? Maybe one replica is destroyed, but the remaining still recovered. That is to ensure the reliability. And also it's kind of scalable. It can handle petabytes of data and grow horizontally. Immediately, one parameter is full, and you can add more hard disk, and can be instruct. So it's optimized for batch processing, not real-time use cases. For the Hadoop, WTS. It's a batch process. So the Hadoop distributed file system model is ideal for write once. You keep the data, you write it, and then you read many times later to do analysis, to also archival data processing or large-scale exact transformer pipeline. Remember, HDFS is a backbone of many other Hadoop ecosystem tools, including like Hive, Peak, or Spark. So these are the tools we read the data from Hadoop distributed file system to do analyze and make decision later on. Next, data lake. A data lake is a modern approach to storing data, especially unstructured and semi-structured format. The key characteristics include the raw data ingestion. Unlike warehouses, the data lakes store data without prior transformation. It kind of schema on read. The data structure is applied only when it reads, allowing flexibility and exploration. This for multiple use cases from analytics and machine learning to archiving. Example including Amazon S3, Sure Data Lake, and Google Cloud Storage also when used with processing tools. A well-designed data lake should help governance, security, metadata management, and lifecycle control. Otherwise, it becomes what they call a data swamp. It's not. It's just unuseful sometimes. Also, we have to have good governance, not just to keep it and to become data swamp. The cloud storage has become dominant mode for big data system due to its scalability and cost effectiveness. Here's some highlights of the cloud-based storage. The first one is the cost tiers. For example, we have the AWS Garcia allows for affordable long-term storage, so it's low cost in option. Second is high durability. Could provide often offer, let's say like what we call is 99s, like 99.999% of the durability. The third one is scalability. You can scale storage up or down based on demand. And actually, the fourth one will be multi-zone availability. Yeah, it's ensure high availability and disaster recovery support. And lastly, is best suited for backup, archival, and also as a data lake backend. So the important note is why the cloud storage is flexible. It must be evaluated based on access latency, and also security and integration with your compute environment. Distributed computing frameworks. Now we have covered storage. Let's talk about the process of the distributed computing framework. There are three key tools that we can apply in distributed computing framework. The first one we call MapReduce. MapReduce come with Hadoop, and the MapReduce is the original batch-oriented framework, reliable but relatively slow due to when it's processed, it connect to hard disk, read and write into the hard disk. So you have some problem with input-output overhead. And then the second one is based on the directed acyclic graph or DAG. We got test, Apache test. Test optimized for directed acyclic graph or DAG. Right. So when we do execution, it's improved the performance of like Hive and other queuing engines. Like Apache Hive also work with test, test, which is then test really fast and doing processing. The next one is Flink. Flink is a tool for do kind of streaming processes. So Flink is using streaming first engine that support real-time processing, event time semantics and stateful computations. So actually also helps like Spark also streaming. So this framework distributed task across cluster, allowing scalable and fault-tolerant data processing. Choosing in the right framework depends on your latency requirements, data volume, and workload type. Could be batch or streaming. Let's go through a little bit more on MapReduce model. MapReduce model introduced by Google and popularized by Hadoop. Now it bundled with Hadoop, and install Hadoop, you have MapReduce tools inside that. It follows simple but very powerful paradigm. The technique in MapReduce, first we split data into chunks that we have already distributed file system in Hadoop. Right? I mean, it's already split the data. And now we have map. The second function is map. Map is a function to transform each data chunk into key values pairs. And then shuffle. Shuffle is the action that we group the data. We group the data together with keys. The key are grouped together. All right. And this redistributed across a cluster. And then the final we reduce. Reduce is the final aggregation. This is performed on each key. Right? So become split, map, shuffle, reduce. So this model is highly scalable and fault tolerant, but it has significant latency also due to the heavy load connect to the hard disk for each stage. So the MapReduce of Hadoop then it's kind of slow, right? But kind of slow. So it's best suited for workloads where throughput is more important than response time, like the log analysis or batch ETL. So modern engine like Spark or Test to overcome MapReduce. This is Spark and Test is working in memory, so it's faster than Hadoop over like probably 100 times in order to process big data. But anyway, the MapReduce, the concept is still applied to many works. Still, it's important. For the test, the Apache test, let's talk more about this. It's the Apache test is a powerful directed acyclic graph based on execution engine design to overcome the latency limitation of the MapReduce. So in test enable graph, typical directed acyclic graph, mean kind of graph when we have node to execute and go to the next node. We go only one way, right? So it's acyclic, no cycle, but acyclic graph execution. So where the task represent at the node, where we have one task, execute and go to the next task, like that. So the next, like a flow, the pipeline, in order to execute many jobs, the analysis. So in this way, it's allow more flexible and efficient workflows compared to the rigid tools such as in MapReduce, Charcoal Reduce, Map, Charcoal and Reduce. In MapReduce, that one is slow level. Now for test technique is more flexible and efficient workflows. So it's tightly integrated with Apache Hive, which is tightly making like a SQL query on Hadoop much faster than test. I mean than MapReduce. So it's more interactive. So test enable query pipeline in memory. So the data transfer and tasks can be used from memory, right? Be closer together, not to go to the hard drive. So in practice, if you running interactive analytics on Hadoop, you can use test under the hood, gives you substantial speed improvement over latency MapReduce. The Apache Flink. So Apache Flink is a stream-first process engine. So we have the purpose-built on real-time data application. So Flink, we have what we call it event time processing, which means it aligns with the computation with the actual time and event occur. So not when it was processed, but during the time it's happened. Right? Event time. And also watermarking, which help manage late arrival data. So we have window function and we move the process, right? And use window function to capture, to manage late arrival data. So, and also is what I call is exactly once semantics. So the meaning that even in the presence of the failure, in this failure, your computation yield correct result with no duplications. It's semantic. And also if this technique support for stateful streaming process, enabling use cases like fraud detection, recommendation system, and alerting. So Flink is a great choice for like low latency, real-time responsiveness, and complex event processing are required. Let's now compare batch and streaming process. Batch is and streaming process are the two fundamental paradigms in big data analytics. What's mean by batch? So batch processing deals with large data set collected over time. So it optimized for throughput, not latency. Think of daily sales support or monthly detail job. So this kind of batch we can do for daily at the night time or monthly at the end of the month during the low workload period, right, that we can do batch processing. But for streaming process, it's handle data in the time that it happened is arrived at the real time. You need to extract knowledge in real time insight. So ideal for flood alerts, right? And to survive the cut. If it's fraud, it have to be alert at that time before it take the money and so on. Or the sensor monitoring or dynamic pricing and so on. Anything that you need to make decision real time at that time that we need to have streaming process. So between batch and streaming, there are key trade-offs. So batch is simpler and fault tolerant, but it's slow, it's delayed, right? It's delayed because we analyze history, not not currently, just history. But streaming, we analyze at that time, but it requires complex engine, right? If you have like a out of order data handling. It's complex, but we need it because we need to deliver instantaneous result, right at the time that we capture. We detect any problem, then we alert immediately before it's severe loss of the money. Sometimes in some application, we can use both paradigms together when necessarily contribute. This is maybe later in Lambda architecture. We talk about this more. Next slide. Lambda architecture, right? The Lambda architecture is a design pattern that combines the best between batch and streaming. So it consists of speed layers, handle real-time data using like Flink or Spark streaming for immediate insight. And also we need to have batch layer perform accurate large-scale processing on the complete data set. Typically used in Hadoop. So we have Hadoop one layer, and we have another layer will be for the real time is a Spark streaming or Flink in order to do real time analytics. And also we have serving layer. This is merge the result and expose them here, the API or dashboard, and display for the end users. So usually for the serving layer can be NoSQL database, to be Cassandra or DB Mongo or HDFS system. Example of the application like Witcher may use in the speed layer, right, to surface trending hashtags in real time, and the batch layer to compute historical engagement metrics. Though it's powerful that the Lambda architecture introduced complexity due to dual code path. So this had led to an alternative like Kappa architecture, which will simplify the design. Next slide is a Hadoop ecosystem overview. So we take a broader look at the Hadoop ecosystem, which comprises multiple tools designed to handle storage, processing, queuing, and analytics at scale. The core components of the Hadoop, we have HDFS, which is storage. Inside Hadoop, we also have Yarn, which is yet another resource negotiator. And also we have the MapReduce core. So Yarn is a resource manager. It's also the job schedule, because we have many CPUs and memory. So Yarn need to manage those, right? And to schedule when we have submitted tasks to processes. So because we maybe have many users or many tasks, and the Yarn can schedule who come first, who is next and so on. And MapReduce is the best processing framework, as we just mentioned. And add on to the tool, we have Hive. Hive is a tool for doing the query for the last data set. It analyze the data on top of Hadoop. Hive is using like same SQL language, so we call Hive SQL. Also, Hive, because sometimes when people would like to do in terms of scripting, right, using pig scripting language. So pig is kind of doing the exact transform load and transform the data and can devour the data like a pig can eating. Like now, you imagine the pig eat the food, right? So you need the tool Apache pig can doing the analyze data very quickly last week. And next tool when we like to store the data, right? Especially when we have to do with together with Hadoop in Hive, and then we can store the result in HDFS. HDFS is a NoSQL column family store for random access and low latency read and write. So these two together allow Hadoop to function as in an integrated big data operating system. The ecosystem contributes to evolve, especially now we move to using Spark better because MapReduce slow, right? So Spark it make work in memory and make faster, and also Apache Kafka. This is so Spark and Apache Kafka is more advanced processing capability. Okay, it's evolving. But anyway, for Jan, which is just another resource negotiator, Jan is the heart of Hadoop ecosystem, right? So yet another resource negotiator acts as the cluster resource management layer. So the key function of the YARN, so it has orchestrate cluster tasks across the cluster, managing CPU, memory for jobs. When we submitted, the user submitted job to ecosystem, and YARN will orchestrate which one will do the job first and which part of memory or which CPU will run which job and so on. It also has the function, the engine called the decoupling of resource management from processing engine, allowing the same infrastructure to run MapReduce, Spark, or test concurrently. It has what we call the multi-tenancy support, which enables different terms of or jobs to share the same hardware infrastructure without interference, without problem. So this abstraction boosts utilization and scalability, fault tolerance. Now, for example, while MapReduce job running in one YARN container, so Spark or Hive requires queries can execute in parallel, but on the others, but all it managed like in centrally. Hadoop itself is not user friendly for querying the data to analyze the data, but when we have Hive and Peak comes, Hive provide kind of SQL-like interface. I mean, when you query to the when you imagine in RDMS, when you query to the database system, right? It's easy with the SQL language. But once you have Hadoop itself, then it's not easy to do the query. But Hive provide SQL-like interface on Hadoop. So then it means we read from Hadoop and we store, right? We store kind of structure like in HDFS. So it supports query. We just written in what we call HiveQL, right? HiveQL or HQL, not S but H, right? HiveQL. We convert the data to MapReduce or test job under the hood. Peak of a data flow, we are what we call the data flow language. We call Pig Latin. Pig Latin is small, suited in the attack transformer pipeline with custom logics. Use cases for distributed this distinction. You can use Hive if your users are familiar with SQL and want to query large data set using JAWS aggregation and filter like in RDMS. We can use Pig for more complex in the procedural data transformation that requires skipping capabilities. So both tools help bridge the gap between traditional BI tools and Hadoop raw power. And now we move on to the Apache Spark. It's a modern, fast in-memory data processing engine that revolutionized big data analytics. Key innovation in Spark. Spark uses what we call is RDD, which is resilient distributed data set. RDD is the resilient distributed data set to hold the data in memory for faster access and fault tolerant because it also copied into the cluster, the different servers in the cluster. So the speed of Spark in analysis is 100 times faster than MapReduce for certain workload to reduce this input-output, read and write. It's really fast. So it leverages the directed acyclic graph like test also, right? We have that's a directed acyclic graph scheduler, which optimizes execution plan for complex tasks. Spark support multiple programming languages. In our case, we use Python. It also have Java or Scala, and integrates well with the entire Hadoop ecosystem. It is now very popular as a de facto standard for big data processing, replacing MapReduce in many organizations now move to Spark. So in our class also we focus much more on the Spark, Python Spark, called PySpark. For the library in Spark or the package in Spark inside. So one of the Spark greatest strengths is its extensive set of built-in libraries, making a unified analytics platform. The first one is Spark SQL. Spark SQL enables structured data processing with data frame. Data frame is familiar with the data frame from last lecture. When we do the lab on pandas, right? And that's when we read the data, got pandas data frame. In Spark, it's also Spark data frame, similar to pandas data frame. And then we can do SQL queries as we have query in RDBS technique, right? In the relational database system. So Spark can do read from the data structure like that, and then keep in the data frame format, and you can do analysis from that. as Spark SQL, then tool for SQL, and as we are maybe familiar with SQL language. This now is you can apply Spark SQL there. But okay, of course, we read the syntax for Spark language. And the second one is MLlib. MLlib. ML is machine learning library. So MLlib is a scalable machine learning library offering classification, regression, clustering, and recommendation algorithm inside. So that you can do a lot of analytics based on the MLlib here. And many applications that can apply in Spark and MLlib. The third one is GraphX, this graph computation. So for the distributed graph computation, think like we have social network or fraud detection and recommendation graph and those things. So they are very popular or very complex tool. So, but graphic can help on this job. It's kind of anything that we have class, structure type. The fourth tools in Spark library, we have the Spark streaming. The Spark streaming is used for real-time data streaming with end-to-end exact ones guarantees. So that's Spark have many tools. So these libraries share a common engine and API style, meaning you can combine streaming, machine learning, SQL analytics in a single pipeline. So this unification simplifies big data development considerably. But if you use some other tool, you may use many tools, right? Like from streaming, one tool, and you have another tool for reading, another tool for doing the processing, and another tool you can do machine learning. But with Spark, you can use all pipeline there, from read the data, streaming come, and then doing analysis, machine learning, and then apply for analytic prediction. Right. So if we compare Spark and Hadoop, Spark is working in memory, right? And Hadoop is using disk-based, like reliable, right? And Spark also supports streaming, right? The use case, if you would like to use real time, of course you have to use Spark, right? But if you have batch, actually Spark can have also lead from batch also, but you can use Hadoop MapReduce heavily on batch only. For streaming, of course, only Spark can do, but no streaming from Hadoop MapReduce. For the fault tolerance, if you need to format, so Spark is kind of RDD and also the elected acyclic graph, so it can be fault tolerance. And Hadoop also they have built-in checkpoint, right? So so Spark is kind of excel on the speed and ease of use and multiple node analytics. You can use also batch or streaming and then have machine learning in the pipeline. So, but for the Hadoop MapReduce is more mature though. It's more because it's come first and it's still used for reliable large-scale batch workloads, especially where the cost is more important than the latency. You can choose Hadoop MapReduce. The modern data architecture often use Spark over Hadoop due to the speed and the versatility of the tools, especially when we have machine learning pipeline and real-time application, then the choice will be Spark instead of Hadoop. Real-world Spark case study. In the world application of Spark, I mean Spark is like Uber search pricing system. Like in the system of Uber, which is usually they have the critical role. They collect real-time GPS data from both riders and drivers. And you can use Spark structured streaming, then the platform in just in terms of we want to process and doing data analysis data instantly, because you need to, the driver and the user can correlate. And so Spark can do correlate user demand and user supply to dynamically adjust fares, what we know as a social price. So why we need Spark in such kind of system? So because Spark is the memory process to ensure ultra low latency. The structured streaming enables continuous computation with high accuracy and exactly one's semantics. It supports scalability. So as Uber operates at global level, processing like millions of events per second. So this gets kind of Spark capability for real time, high impact, and in Uber decision making in modern digital platform. NoSQL database category. Now we like to turn to the NoSQL database is essential for managing the variety of and scale of the big data. NoSQL system are designed for we call this horizontal scalability and schema, also flexible schema, not like in the relational database system. In which we have to define what are the attributes of the database, and we have many tables in the database, and what are the attributes or the key decide to optimize on before we can implement the system. But with NoSQL, we don't need to worry about those schemas. And factual schema we can apply immediately on the use. Right. So and also in NoSQL they have high availability over the consistency in some cases. So there are many types of the NoSQL database. Usually we classify with 4 major categories. The first one called document storage. Like in example for MongoDB, we store semi-structured like JSON like data. The second group is called key value storage. Like we have Redis optimized for ultra fast key-based lookup. The next one is column family storage, which is Cassandra or HDFS. So this kind of NoSQL storage, the large scale time series and wide column workload. And the fourth group is graph database like Neo4j. It's built for modeling and querying network relationship. So these databases chosen based on access pattern and a data model for application. Let's go to the document storage type, which is a popular form of NoSQL. So this system manages the data in the JSON format or BSON format. So they support flexible and dynamic schemas, allowing different documents in the same collection to have different fields. And an example of document storage are the MongoDB, CouchDB, is a leading example. And the use cases in document storage we can apply in content management system, IoT data encryption, products catalogs in e-commerce. The strength of document databases lies in their ability to mirror application objects directly, that simplify um, development processes and reducing object relation mapping complexity. The second group, key value storage, are the simplest form of NoSQL database and among the fastest also. So the data is stored as key value pairs with no predefined schema. This makes them perfect for applications requiring rapid lookups or caching or the session state management. Example of key value storage is Redis. This is an in-memory key value store with support for data structure like list, sets, and hashes. Also, we have Amazon DynamoDB, and manage key value store with high durability and availability. Due to their simplicity and speed, key value store are often used as a complement to other systems for performance optimization. So the third group is a column family store, provide a more structured NoSQL approach designed for scalability and efficiency in analytical queries. The key traits of the column family stores: data is stored in a wide load, where each row can have different set of columns. Right. So this system optimized for read and write and doing performance across massive data set and best used for time series and logs and recommendation system. Example of this group is Apache Cassandra. Apache Cassandra is highly available and partition tolerant, used by Netflix, Instagram, and many more. Another one is HDFS. HDFS is a Hadoop native store that integrates with HDFS and support large tables with sparse data. So the column family stores provides a columnar access pattern of data warehouse while maintaining the horizontal scalability of NoSQL system. The graph databases, the fourth one. Graph databases are purpose-built to model relationship and network like data. So they represent data as node. Right? Node is sometimes called entity, and we have link to the next node where we have the relationship or edges of the graph. So this structure is ideal for highly connected domain like social network, recommender system, recommender engines, fraud detection. Example of this group, we have Neo4j, Amazon Neptune. This group, like Neo4j is the most well-known graph database with cipher query language. Neptune managed graph database support in Spark QL, SPARQL, and also Gremlin. Unlike relational databases where complex joins are needed, graph database can traverse connection efficiently, enabling deep link analysis in real time. To understand a trade-off in NoSQL design, we must understand the CAP theorem, CAP. The capture limit, also known called Brewer theorem, Brewer theorem. They have three key terms: consistency, availability, and partition tolerance. Right. The consistency is allow all nodes see the same data at the same time. Consistency. For the availabilities, every request receive a non-error response. Right? It's always available, not is always available. Right? So every request receive a non-error response. The third one is a partition tolerance. The system continues to operate even if network partition occurs. Right? So it's, and the theorem is that the theorem is there are two of the three guarantee at the same time. You cannot have three, just only two. Choose two out of three at the same time. So you mean that not possible to have three at the same time. So it's impact NoSQL database design. Because network partition are inevitable in distributed system, NoSQL database often choose like availability and partition tolerance. So we have A and P. So this group we have Cassandra or Dynamo that have two features for availability and partition tolerance or AP. Or if you would like to design for consistency plus partition, you can choose like HBase and MongoDB. When configured, install strong design for strong consistency. You have to choose MongoDB or HBase. So understand the capture and the key is to select the right NoSQL database for your workload. How about NoSQL and relational database? Right. Let's compare the NoSQL and relational database management system or RDBMS. So let's say the schema. The schema, NoSQL is kind of schemaless. Right? It's dynamic. But if you choose the database like RDBMS, that is fixed schema. You have to design the table and columns, and you have to identify what are the keys and how it's connected together between the tables. Right? So if you need no schema or schemaless like or dynamic schema, you use NoSQL. For scalability, NoSQL is kind of horizontal scale. It means you can add more and more hard disk without problem. But for DB RDNS, usually with vertical between, you have to define, I mean, the has this size at the beginning and keep grow in a vertical scalability. For consistency, NoSQL has like we said that we have to choose which one that is consistency, but usually RDNS have strong consistency. So you need to consider which one is more suitable for your work. For use case like when you have big data, IoT, real-time application, then choose NoSQL. For you have use case like you have to use structured data or application like online transaction processing or OLTP job, then we chose the RDBMS. Right. So NoSQL is excelled in high scalability, especially for distributed application, flexible data model, ideal for semi-structured or unstructured data, and support use cases like real-time analytics, IoT, and social data. But RDMS still dominates, right? When you have the what we call the you have to optimize your your work, right, to query in like the banking or enterprise software system or any complex join and so on. So RDBS have to be applied for that. So you need you cannot say that you're gonna use which one better, but you have to consider your application, what type of database that you need in your job. It may be best, depend on what kind of work you have. Okay, move on to real-time data processing. Apache Kafka. This is one of the fundamental tools in modern data pipeline. Kafka is a distributed publish subscribe or PubSub platform designed to handle millions of events per second. So with durable logs of storage allowing repairable streams. So Kafka is act as a high throughput fault tolerance buffer between producer and consumer. In Kafka, producer and consumer. Its advantage is include scalability, fault tolerance, integration with stream processors like Flink, Spark, and Storm. That are the streaming processor. Kafka is widely used for real-time ingestion, log aggregation, and as the backbone of event-driven architecture. Kafka is used across industry for diverse real-time applications like log aggregation. In log aggregation, centralized logs from distributed services often pipe into so-called ELK, which is this, the one that we use in the big data. And also we have the metrics pipeline, the stream operational metrics to real-time monitoring system, and the streaming process inputs act as a source for Flink and Spark streaming jobs. Or website activity tracking, we capture click streams and user behavior for personalization and analytics. Kafka decoupled architecture makes it ideal for loosely coupled scalable system. Producer and consumer doesn't need to be aware of each other. Kafka handle they handle the persistence and delivery. Let's now look under the hood at the Kafka architecture. So Kafka made up of the foreign core components. The top categories of feed to which they call publish. The partition. Each topic is split into partition for scalability and parallelism. The producer is an application that sends data or events to Kafka topics. And we have broker Brokers, Kafka server that manage topics and partition. Each broker has multiple partitions, and also it has consumer. Consumer is an application that read data from Kafka, and also optional we have Zookeeper that used to manage Kafka cluster, coordinates reader elections, and track the broker health. Or the other option can be KLab that can be used. Alright. So this is user cluster with brokers, many brokers inside there. Because serve as a manage topics partition. So topic partition here. We have the streamings there. So together these components form a scalable high throughput massive messaging system. So Kafka log-based design means it can persist even for a long time and serve both real-time and batch consumer in the same time. Now let's revisit Apache Flink. So this time focusing on specifically on the streaming capability. Flink supports state stream process with in-memory state that is fault tolerant and exactly once consistent. Exact one semantics, which enable no data. Ensure, right? When exactly one semantic is ensure no data is lost during the process or duplicate. Did not duplicate or lost. Essentially for financial or transactional system. And it has feature for low latency computation, making it suitable for responsive analytics, monitoring, and alerts. So actually the production in real application, Flink is used for like fraud detection system, sensor data processing in IoT or in the real-time customer interaction platform for its tight integration with Kafka and support for watermark and complex event pattern makes Flink ideal for mission critical stream pipeline. Understanding the distribution between event time and processing time is critical for accurate stream analytics. So the event time is the actual time when the event occurs. Like user click a button, that is event time. The processing time is the time the event was ingested and processed by system. So the processing time is equal to system arrival. So why it is important that event can arrive out of order due to the network delay or retries. So if we rely only on processing time, we risk introducing bias or incorrect application. So to solve this, Flink or similar engine use watermarks. They help estimate event time, progress, enable window operation, snapping windows, like tumbling, sliding window, even with late data. So this concept ensures accuracy in real-time dashboard alerting system and data compliance report. Window application. In streaming process, window application that us divide considers data stream into manageable chunk analysis. So there are three main window type. Thumbing window. The thumbing window is a fixed size non-overlapping. We count the number of transactions for every 5 minutes without overlap. 0 to 5, 5 to 6 to 10, and so on. Sliding window actually fixed size and then we overlap. Slide window, slide over time. And rolling, we're using rolling overlap average. Every minute it's 3-second overlap. And so the third one is session window. So based on user activities or inactivity, like group clicks within a session ending after 10 minutes or inactivity. That's called the session window. Winnowing is crucial in turning infinite stream into bounded computation. It's extensively used in IoT analytics, user behavior modeling, financial data summarization. Let's discuss about Amazon Kinesis, a full managed service from Amazon service for real-time streaming data ingestion. The core features designed for scalable, durable, and fault-tolerant ingestion of streaming data. Integrates with NVS services like Lambda, which is used for event processing, and also S3 storage and Redshift analytics. It's also enabled for real-time dashboard, alerting, and machine learning workflow. The Kinesis support data streaming for custom app development. The Kinesis file host is for the automatic deliver to storage services, and Kinesis analytics for SQL-based stream process. Amazon's answer to Kafka plus Flink, but for open source, Kafka and Flink, but if you use Amazon, you use Kinesis. So the Kinesis is a widely used cloud-native streaming process in data-driven enterprise. But if you are in enterprise and you have money and use cloud in Amazon. Let's see some example like in streaming case in Netflix. This is the real-world streaming architecture of Netflix. Netflix uses combination of Kafka for real-time data ingestion and use Apache Flink for the stream processing and analytics, and use Cassandra, Apache Cassandra for fast scalable storage of the streaming output. So this architecture enable real-time recommendation system, dynamic personalized based on user behavior, streaming analytics for performance and user experience optimization. For example, as soon as a user watches or stop a video, events are streamed to Kafka, processed by Flink, and stored in Cassandra immediately. Inferencing then what the content is recommended next. So this demonstrates the power of end-to-end real-time pipeline for enhancing business outcome and user satisfaction. Now we turn to the Lambda architecture. Now with the specific technology mapped to its layer. The first layer is speed layer. The speed layer uses tools like Flink or Spark streaming. It handles real-time events, real-time for immediately insight. In the batch layer, run periodic high throughput jobs on historical data. Better use Hadoop. And then in the serving layer integrates and exposes result to consumer, often using NoSQL database like Cassandra or HDFS. These layered approach ensure low latency responses from speed layer. There is a complete output from the batch layer, and it has high availability and redundancy across the stacks. So while powerful, this model requires maintaining two different code bases, which had led to emergence of simpler alternative like Kappa architecture. That is the next one. So Kappa architecture is a simplified version of Lambda stream only architecture designed to eliminate the dual path complexity. Key principle of the Kappa architecture is a single stream process engine, such as Flink or Kappa streams. The processing is done by replaying data stream from Kafka, and the batch is treated as a special case of streaming. So advantage of this Kafka model or Kafka architecture is simple maintenance with one code path. Easier to scale and update, suitable for organization with real time is the default. So it's widely adopted in microservices, sensor network, and modern data platform where latency is critical and even logs persistency stored. The ETL for big data. ETL is a mean extract, transform, load workflow in the big data system. ETL traditional involves we extract the data from multiple heterogeneous sources, and then we transform the data into the required formats using tools like Spark SQL or Python, and load it into target system, typically data lakes or data warehouse in the big data ecosystem. The key characteristic in the big data ETL is a parallel processing of transformation, integration with structure and understructured sources. It's handle data as rest, data at rest, and data in motion. Spark is often used as a transformation engine due to its scalability, speed, and support for advanced analytics, including like machine learning pre-processing steps. The ETL approach as an alternative to ETL, many modern architecture now favor ETL, exact load transform, BLT, right? Instead of ETL, now we use ELT, exact load transform. Here's how it works. First, we extract data from sources, load it directly into data lake or warehouse, transform it on demand during query time. So advantage of ELT is the schema on read, allow flexibility, enable ad hoc analytics on raw data, suit modern storage system like S3 or BigQuery or Snowflake. This approach aligns with data lakehouse strategies and is especially effective when using platforms like Databricks or AWS at China, where transformation are applied dynamically at scale. Now, we shift our attention to big data in the cloud, which has become the default architecture for many organizations. The key characteristic of the big data on the cloud is the elastic scaling. Resources can automatically scale up or down based on workload, reducing cost and improving agility. And managed services provider like AWS, EMR, Elastic MapReduce, right, EMR, Google Cloud Data Plug, and Azure HD Insight offer fully managed Hadoop Spark cluster, reducing operational overhead. And it's using the model for pay-per-use pricing. You only pay for what you consume, ideal for a regular workload or experimentation. So cloud platform also support hybrid deployments, allowing seamless integration with on-premise system. The key takeaway is that the cloud enables rapid, flexible, and cost-effective big data infrastructure deployment. Now let's look at the Apache Unify tool for data flow automation in big data pipelines. The key features of Apache Unify is if kind of visual interface. We kind of drag and drop GUI design complex pipeline. This is kind of real time and batch support, handle streaming and static data set. Data provenance is track how data flows through the system, and back pressure and prioritization ensure stable performance under load. So NIFI is particularly useful for data ingestion from IoT devices, log collection and routing, integrating a disparate system without coding. So think of NIFI as a data traffic controller that orchestrates flow across sensor databases, cloud storage, and analytics engines. Let's discuss how we visualize big data in real time. The popular tools include Kafka, which is ideal for the time series data visualization, especially metrics from Prometheus, InfluxDB, or Kafka. The next one is Apache Superset. Apache Superset is a SQL native BI tools for dashboard on top of big data engine like Crystal or Hive. So these dashboards support auto refresh, enable live monitoring of KPIs, can integrate with the team processor to update charts and verify in milliseconds, provide role-based access, real-time alert, and custom visualization. So they are widely used in operation centers, executive dashboard, and performance monitoring system. Next, the DataOps. DataOps apply DevOps principle to data engineering, promoting agility, automation, and governance in analytics workflows. The core concept include CI/CD for data, automate ingestion, transformation, and deployment. CI is continuous improvement, CD is continuous deployment. It's like in DevOps. The version pipeline, right, like Git for data flow, so allowing reproducibility and rollbacks in the version pipeline. In testing, so we validate the other quality, schema compliance, and pipeline logics, and correlation. Encourage cross-functional teamwork between data engineer, analytics, and data scientists in order to work together. By formalizing the development practice, DataOps ensure reliable, fast, and datable delivery of data products critical for regulated industries and machine learning pipeline. Next, the managing metadata. Metadata is the data about data, and managing it is essential for governance, discovery, and lineage. Techniques and tools include data catalogs like Apache Atlas, right? Amundsen, or Data Hub. So that documents schema, ownership, and quality metrics. Lineage tracking to understand how data flow through the system and to identify dependency. The impact analysis is to assess what downstream assets are affected when data structures change. So metadata management underpin data quality compliance, like PDPA or GDPR, and trust. It enables user to find, understand, and use data efficiently, like in transforming data lakes to from swarms into organized, valuable, and repositories. A monitoring big data system is essential to maintain performance, availability, and reliability of big data system. The key components include metrics like we tracking system throughput, latency, resource users like CPU, memory, disk I/O, and job duration. Used for metric use is used for capacity planning and bottleneck analysis. Loggings. Logging is centralized by ELK stacks. ELK stand for Elasticsearch Log Stacks and Kibana. Logging helps in debugging, auditing, and tracing system behavior. Alerting. The tool like Prometheus plus Grafana can trigger real-time alerts for anomalies or threshold violation. Ensure a quick response to failure or degradation. So proper monitoring avoids downtime, improve service level agreement or SA, and also compliance, as well as the facilitates root cause analysis across distributed systems. Security is non-negotiable in big data development, especially given the volume and sensitivity of the data being processed. So the key consideration First one is encryption. Data at rest. Encryption protects file stores in HDFS, S3, or cloud databases. Data in transit encryption. That is one ensures secure communication between nodes. Encryption is really important. Also, in authentication, can use Kebelos, which is widely used in Hadoop-based system, and also cloud-native IAM. IAM is Identity and Access Management. Cloud-native IAM system help enforce policies across services. Then next one is access control, like role-based access control, RBAC. RBAC ensures only authorized user can read, write, or execute. Fine-grained access is essential in shared environments. Security must be embedded into every layer network, storage, processing, and access. Governance compliance. Data governance ensures that data is accurate, secure, and compliant with legal and organizational standards. Important component is regulation, compliance like PDPA or GDPR and SIPAA requires accountability in how data is collected, stored, and used. Audit trails need to track who access what, when, and why. Policy enforcement, like data retention, anonymization, and consent policies must be enforced via automated workflows. So linear tracking essential for impact analysis and demonstrate compliance during audits. So good governance build trust, enable reusability, and reduce legal and reputational risk. Okay. Despite its advantages, implementing big data solution presents severe challenges, like data silos is isolated data sources, impede integration and insight. High velocity integration is a difficulty in capturing and processing data in real time without loss. There is storage cost. When you have petabytes of data, the petabyte scale data storage is expensive, particularly when retention policies are unclear. First one is integration complexity. The connecting of the heterogeneous system, like legacy databases, cloud service, and streaming platform requires carefully orchestration. The successful project must prioritize architecture, data quality, and cross-functional collaboration to mitigate these issues. Finally, let's discuss on some emerging trends that are reshaping the future of big data. Data mesh architecture, decentralized ownership of data by the domain teams, treating data as a product, promotes scalability and data democratization. Machine learning plus streaming integration. So real-time predictive analytics using live data streams. It enables application like anomaly detection, fraud prevention, or hyper-personalization. Another one challenge is a serverless big data platform. Tools like AWS, Athena, Google BigQuery, or Azure Synapse remove infrastructure management. Have serverless big data platform. So its focus shifts to query logic and insight with automatic scaling and cost optimization. So this innovation reflects a shift from managing infrastructure to managing insight, a core goal of next generation data stream. Okay, let's see example how big data is transforming healthcare, where the timely insight can save life. Key application like IoT monitoring. Wearable devices collect real-time vital signals such as heart rate, blood pressure, and oxygen situation. We can use a steam into the signal stream to the platform for early detection of abnormalities. They have the real-time alert. The abnormal reading can trigger alert for physician or emergency response teams, powered by stream processing engine like Flink or Spark streaming. So we can use historical patient data stored in NoSQL system for fast retrieval, enable personalized medical medicine, and AI-driven diagnostics. So challenges include like data privacy, as we have the law PDPA, GDPR, HIPAA compliance, interoperability, and system latency. But the payoff is improved care and operational efficiencies. For industry use case like finance, in finance the stack up high, so benefit of big data analytics. Top use case like real-time fraud detection, like when we have transaction data, let's say from swapping the card, credit card, the data is analyzed instantly and flag suspicious activities. Techniques include anomaly detection using machine learning models to also rule-based system. Or we can use like the application in list scoring, the credit list, market list, or operational list quantified using historical plus streaming data. Model update in real time to reflect market condition. High-speed trading analytics. System ingest market feed and react in milliseconds using event-driven architectures. Latency optimization is critical, handled through in-memory database and stream analytics. Security, precision, and compliance. That's based on the Basel 3 SOC. Major concern in this domain. For application in industry use case, smart city, right? Big data is central to smart city initiative that aim to optimize urban life. Key implementation is like traffic flow optimization, where the sensor on roads, vehicles, and signals feed into analytic system. The real-time data help us light timing, reduce congestion, and suggest alternative routes. Or like in environmental sensors, you can monitor air quality, noise level, and weather condition. Data drive public health alerts and environmental policy adjustment. And also in the emergency response, social media call requests and sensor alerts are integrated into dispatch resources efficiently. Pattern recognition and predictive analytics assist in crisis prevention. The smart city rely on interoperability, low latency platform that combine cloud, edge, and AI to make data actionable at scale. Okay, today we have the labs on the, so we can design the pipeline, data pipeline for ride sharing, ride sharing data pipeline. So we're gonna have input from GPS, user data payment, and also we require for the low latency scalability. Right? The tools use, we're gonna use Kafka Spark Cassandra. So this lab going to be we are using Docker and Docker Compose environment. Right. So let's see you in the lab. Okay, and then for this is at the end of the lecture 3 theory part. So we're going to move on to the lab part. So this lab will help you to understand the integration of multiple tools, architecture design, and trade-off in real world with big data pipeline. Okay, see you then.